Okay, so let's take a look at 205, 2C. So it says determine the critical points for each function and use the second derivative test to decide if the point is a local maximum or a local minimum, or neither. Okay, so 2C is S is equal to T plus T to the negative 1. All right. So first thing we have to do here is determine where this derivative is equal to 0. And then from there, use the second derivative to determine whether it's a maximum or minimum. So I'll start by finding the first derivative, make sure there actually are critical points. Okay, so S prime is equal to 1 plus, and then here we have negative 1 times T to the negative 2. All right. So at this point here, since we want to solve for when the derivative is equal to 0, I should really do a little bit of simplifying here. So this will be 1 minus 1 over t squared. Okay, and so here we'll, hold on, some people coming in. Okay, so what do we have here? We have t squared minus 1 over t squared. All right, so this actually is not so bad because we see that my critical numbers are going to be at plus or minus 1. Okay, now normally we would set up our number line and test the first and second, test the derivative on either side, but we're going to use the second derivative test here. So not even going to bother doing that. These are the only places where I might find local extrema. So now I'm going to use the second derivative to help me determine that. So here, notice how I'm going to use this version of the derivative to take it, as opposed to this one here, which is going to be a lot more complicated. So here, if I take S double prime, well, that's just equal to 0. So here I've got my negative, and now I've just got negative 2 times t to the negative 3. Okay, and this saves me a lot of time now because what I have is 2 over t cubed, and this is going to be very easy to determine the value of the second derivative. In fact, the only thing I really care about is the sign. Okay, so S double prime at positive 1. Okay, put this into here, and I see I'm going to have 2 over 1, and it's greater than 0. That's really the only thing I need to know. I'm not that interested in what the actual value is. And then when we take S double prime at negative 1, well, here, negative 1 cubed is still going to be negative, so this is going to be less than 0. All right, so at this point, I can now make my conclusion that what we have is A, so at 1, at t equals 1, our first derivative is 0, and our second derivative is positive, so that means opens upward, so we have a local min. Okay, and let me just check if they're just looking for the they're looking for the actual critical points. So I guess I'll have to actually find that point, and then at t equals negative 1, since it's concave down, we know we have a local max. Okay, and so now I'll just put this in. So here we have 1, and what do we have? Well, 1 plus 1 over 1 is just going to be 2. Okay, and then here, 1 over negative 1 is going to be negative 1, so 1 minus 1, so it's just going to be, looks like it's going to be 0. All right, so here we have our critical points, and we have their characteristic of being either local min or local max. All right, any questions on this one here? So to whomever asked the question, so here I just, again, found the derivative, found my critical points where the derivative is equal to 0. Shouldn't the second point be negative 1? Oh, thank you. Yeah, good catch. There you go. Okay, and then from there, tested the sign at each of those values to determine local min and max. All right. Now recall that what we saw today is sometimes this, the second derivative test could even come into play when you're given information graphically. Okay, because that holds under all circumstances. In this case here, we just happen to have the analytical model. All right, any questions, or we move on? All right, so let's move on to the next one is page 213, number 4D. page 213. Yep.
Tony, sorry, I have a question.
Yep.
For the local max, I got -2. I'm not. Did you mention something about that? It's supposed to be 1 comma -1 comma 2 or
Well, here I did in my head. Hopefully I did it okay. So here, when I have t to the -1, that's just 1 over t. So 1 over -1 is -1, and then -1. Oh, why didn't somebody yeah, you're right.
yeah,
Here, it's not
yeah.
1 minus 1, it's -1 minus 1. So this is
Yeah.
-2. Oh, lots of people let me get away with that. Okay, and this is, you see, I made that error that I tell you folks not to make, as I just did something quickly in my head, and there you go, I just lost half a mark. Whereas if I just, written it out or stuck it in my calculator, I wouldn't have made that mistake. Okay, good catch on that, and not good for the other 20 people. Okay. All right, 213, number 4D. All right, so 4D says, use the algorithm for curve sketching to sketch the following. Okay, so let me just ask here if the problem was not being able to find the x-intercepts. To the person who
Yeah,
asked
for me
that.
it was.
Yeah, and so essentially, I guess I didn't notice that when you can't find the x-intercepts easily on this one here, other than at x equals 0. But what you can do is go through the whole process of the curve sketching algorithm, and you should still probably be able to draw a reasonable graph even without necessarily all the intercepts. But for sure, you're going to be missing some information. So sorry, I just assumed since they gave that function that it would work out relatively nicely. Okay. So in the end, if that was the only, do you still want me to go through it? I'm happy to go through it. And I would just draw it without necessarily knowing the x-intercepts.
Oh no, that was the only issue for me. You don't have to
Yeah.
go through it.
Okay, so we'll skip that one then. Okay, sorry about that. Like I said, I assumed the book would have chosen examples where those would have been easy to find. All right. So let us go to assignment. So part A, 12D on the unit assignment. So this says sketch the following using suitable techniques. All right. So this is unit 3 assignment number A 12D. All right. So let's see what this would look like. So we've got our function here, which is y equals 3x squared ln x. All right. And so now let's go through our process. Now, Arthur, I see your hand up. Is that a legacy hand, or was there something you to ask?
It is a legacy hand.
All right. All right. So let's start with this here. So again, step 1 is I'm going to take everything I can get regarding the function itself. And let's start with the domain. Now here, obviously 3x squared has no restrictions, but ln x does have a restriction. X has to be greater than 0. Okay, so my domain is going to be 0 to positive infinity. All right. Let's find any x-intercepts. So here, obviously, if x equals 0, then the whole thing should be equal to 0, but 0 is not actually in my domain. So it looks like there's no x-intercepts from the first one, but of course, I was going to go too quickly there, ln x can be equal to 0, and that happens when x is equal to 1. So we only have that one x-intercept. All right. We can't have any y-intercept. So this is the one where we can't have any y-intercept because obviously x cannot be equal to 0. Okay. Now, doesn't look like there's going to be necessarily any vertical asymptotes sort of in the middle of the function, but we know that since this function ends at 0, all right, and is not a value, doesn't have a value at 0, we should do some investigation there. Okay, but before I do that, let's find the end behavior on the right-hand side. So the limit as x approaches positive infinity of this function, well, 3x squared is getting really, really big. Ln x is getting really, really big, and I'm multiplying these two big positive numbers. So that's nice and easy. I know that's going to be going to positive infinity. But where I have to do a little bit of thinking here, and this I suspect will be similar to the ones we saw, is to see what happens to this function as x approaches 0 from the right. Okay. Now this is where, if you want to draw yourself a little diagram to help you out, well, we know that x squared is approaching 0 and ln x is approaching negative infinity. And this is similar to the discussion I think we probably had for one of them in class, is the x squared approaches 0 faster than ln x approaches negative infinity. Okay, so based on our hierarchy for speed of growth and decay, okay, we know that this is the function that's going to win out, hence it's going to approach 0. Now notice here it's going to approach 0, it won't won't necessarily get there because obviously x never gets to 0. All right, and now the last thing we'll do is determine our sign. Okay, so I'm going to start at x equals 0 since I'm not interested in anything else. And so here the only thing I need to check is at x equals 1. All right, so if I put in a number between 0 and 1, say 0.5, 3x squared is going to be positive, but ln x, we know, crosses at 1. So it's going to be positive times negative is negative. And then here, when I take something bigger than 1, so 3x squared again will be positive, but say something like ln 2, okay, since it's bigger than 1, is going to be positive. So positive times positive is positive. All right, so any questions on what I was able to determine from the function itself? No? Okay, so now let's move to part 2, which is going to be what I can get from the first derivative. So the first thing I have to do is find the first derivative. So y prime is equal to, so here, the 3 is just a constant, so I'll leave it out. So derivative x squared is 2x times ln x. And then here we have plus x squared times derivative of ln x is 1 over x. Okay, so please make sure you're checking my algebra as I go along so we don't find the error later. So here, what do we have? We've got 3 times, so this is going to be x here. So I'm going to take out the common factor of x. All right. And what are we left with now? We're just left with 2 ln x, and it looks like plus 1. Okay. And so what we want to do is determine when this is equal to 0. Okay. So obviously we have x equals 0 would make the whole thing 0, but that's not in the domain. So I'm not going to consider it. So the only other thing I have to consider here is when 2 ln x plus 1 is equal to 0. And so I'm just going to solve this. Ln x is equal to negative 1/2. And now turn it into exponential form. So x, the result, is equal to the base e to the exponent of negative 1/2. Okay. And let me find a calculator here, and I might as well determine an approximation for that. So here I got e to the exponent of negative 0.5, okay, is about 0.6. And you notice here, my graph can't be very accurate. So I'm just going to keep 1 decimal place, okay? And so now we just have to figure out, is this going to be max, min, or neither? So we look at f prime again. I'm going to start at 0. And so the only place I have to look at here is 0.6. Okay. So I know this first part is going to be positive. So let me just stick in 0.1. So 2 times, ln of 0.1 plus 1, okay, is negative. And then if I stick in x equals 1, Well, that one's easy to do because we have ln of 1 is 0, 0 plus 1 is going to be positive. Okay, so since I'm going from decreasing to increasing, this means we have a local min. All right, and now let me actually get my point. So we've got 0.6. And again, I'm even just going to put 0.6 in my function because I don't really need to worry about being super precise when I'm putting this on a graph. All right. However, if I was being asked specifically, find the point at which is a local minimum or local maximum, then I would be putting in e to the -1/2 into my equation and being more precise. But here, since this is just part of a curve sketching question, I'm not going to worry about that. So we've got 3 times 0.6 squared. Okay, it'd be good if other people are doing this with me so you can check that I didn't make any silly mistake, times ln of 0.6. Okay, so it looks like it's about -0.55. Since 55 is really right in between, maybe I will keep both numbers there. All right, so any questions on what we can get from the first derivative? No. All right, so let's move on to the last portion, what we can get from the second derivative. All right, so here I'm just trying to see where I'd have I mean, honestly, I'm not sure. They kind of both look, I guess this is a little simpler working from this one here. So I'll use that one, although it's probably a toss-up as to which would be easier. Okay, so I still have this constant of 3. Okay, so now when I take the derivative of this portion, okay, derivative of 2x is 2 times ln x. Okay, and then plus 2x times the derivative of ln x, which is 1 over x, and then plus the derivative of x, which is 1. Okay. So now let's simplify that before I do anything with it. So I see here that I've got 3 times, so I've got 2 ln x, and then here the x's cancel out. So I just end up with 2 plus 1. Okay, which is not so bad. All right, so make that equal to 0. And so now I'm left with ln x can be equal to -3 over 2. And so again, switch it into exponential form. So x is equal to e to the -3 over 2. And again, I'm going to stick that in my calculator. Okay, e to the -3 over 2. Okay, and that's about 0.22. All right, and let's check our signs to see if this is indeed a point of inflection or not. All right, so 0.22. So let me again put, say, 0.1 here. So let's do the 3 I don't need to worry about. So 2 times ln of 0.1, okay, plus 3 is negative. And then here, let me just put 1. So 2 times ln of 1, obviously 0, plus 3. So this is positive. So we do have a point of inflection. All right, and at 0.22, and let's put that into our function now to get the y value. So 3 times 0.22 squared times ln of 0.22. And it looks like it's about, well, -0.22. All right. So any questions on this here so far? Okay, so again, I'm counting on you. I'm kind of doing this very quick and talking. I hope everybody has been checking my work as I went along. All right. So now let's set up our graph, and I'm just going to do it by hand here. But what do we have? So we have an x-intercept at 1. My important x values are all very, very small. My important y values are small and negative. So I guess it makes sense to leave myself a lot of room on this side, since greater than 0. Okay. And here, do I have any positive y values at all to work with? If I take a look, no, not really. So I'm going to put this fairly high up here. Okay. And I know I need to get to x equals 1. So I'll put 1 there. And I've got my x-intercept. All right. And I'll put like -1, somewhere down here, because these numbers are very small. Okay, so let's put the local maximum, local minimum. So that's at about 0.6, and that's a little further than the middle here. Okay, and where's my point of inflection? My point of inflection is at 0.22, so a little less than a quarter, -0.22. So somewhere there is my point of inflection. Okay, so now what I have is that from this point here all the way there, I know is going to be always concave up. So this is pretty easy to draw. So I'm going to make sure I draw it concave up, going to positive infinity. But in this portion here, I see that my function is going to be concave down. I know it's going to be approaching 0. I want to make sure that I put a hole there to show that I'm not including that point. But I want to kind of draw the function so that it definitely looks concave down in that area. All right. So quite a bit of work to really not get a lot of information, but what we do have now is seemingly, a good idea of exactly the shape and the curvature of this function. All right. So like I said, even though maybe this doesn't look like the nicest transition, I really want to make sure it's obvious that I've transitioned from concave down to concave up for the rest of the function. All right. Any questions on this here? So this was, I would say, a little, slightly on the long side, but, this is why one of your graphs will involve having you taking the derivatives, whereas the other one is just going to involve the analysis portion. Okay. So you kind of have to juggle being precise and careful with also a certain amount of speed. All right, any questions on this? Would we be taking a derivative of a function like this? Yeah, this one's not so bad. I wouldn't say this one's too bad, As long as you're careful here. Look how nicely the derivatives simplified and relatively easily, I would say. So yeah, this wouldn't be out of left field if I gave you something like that. Okay. Anything else we want to ask about this?
Yeah, Tony.
Yep.
I remember, I have two questions. I remember
Yep.
earlier you talked about like the functions speeding up and slowing down, like which one's faster. What does that determine again? I just wanted some clarification.
Are you talking about when we were talking about
The beginning part
like
one.
speed or are you talking about this
Yeah, like
question?
part one of this question.
Is here when I was trying to determine how this function was going to behave near 0. Because when I look at the individual components, as x gets close to 0, this first part is approaching 0, and this second part is going to negative infinity. So it's not clear how that multiplication is going to turn out. So this is where I have to think about our hierarchy of which functions grow faster than others or decrease faster than others. And what we know is that polynomials, okay, change quicker than logarithmic functions. So that's why when I'm multiplying this big number, when I'm multiplying this number close to 0 by this number that's getting close to negative infinity, okay, this is the one that's approaching 0 faster than this one is approaching negative infinity. Okay.
Okay, so
So that's why the end result is that this function is approaching 0 and not negative infinity. Okay. And the best example I can give you there is, let's say I have a number that's close to 0. Let's say that number close to 0 is 0.1. And I multiply something that's very, very negative. So negative 10 to the 6. Okay. Small number close to infinity. Good. Oh, look at that. It's still a very small number going towards infinity. Okay. But what if my number that's close to 0, instead of being 0.1, is 0.00000000001, and I multiply that again by negative 10 to the 6? What happens when I multiply these two numbers? Oh, the result is very close to 0. Okay. So one thing I could have done is just put in a number real close to 0 into both of these, say 0.00001, and see what the end result was going to be. Or I could just remember that, oh, polynomials change faster than logarithmic functions. So when I'm multiplying a number close to 0 by something that's going to negative infinity, because the x squared is the one that takes over, the end result is that it's going to be approaching 0. Okay.
Oh, okay, that sort of helped me out. I'm just really confused on when we should be like doing this.
The only reason why I'm doing this here is because the function doesn't go all the way to negative infinity. It stops at 0. So I need to know what's happening near 0. So it's not like it's approaching a point, because it's not defined at 0. So don't we need to know whether here, is it coming down and going to negative infinity? Is it approaching 0? Is it approaching some other number? So that's why in this particular circumstance, because the function isn't defined all the way to negative infinity, that I consider this limit here. Okay. So that's my reasoning as to why I'm doing it. Okay.
Okay, I'll ask more questions maybe tomorrow because I'm still
Okay.
not understanding fully, but
Yeah.
thank you for
Okay.
the clarification.
Yeah. Well, let it stew for a bit and then you can ask tomorrow.
Yeah.
Okay. Anybody else? Okay. So the other two questions I have here are A7 and A10. So like I said, there are full videos on that, but maybe we can take a quick look, and maybe the people who asked them can ask specifically what the issue was. Okay, so A7 was determine the points of inflection of each of the following. Oh, 7A, by the way, the answers, so I took this from a textbook. The answers are missing. It looks like it's missing one of the points of inflection. There's also a point of inflection at positive e to the 3/2. So I think you'll see it in the video. Was that the issue with 7A? Whoever asked that? I think Philip.
No, I think I just got lost, I think like midway through with like trying to find the points of inflection.
Okay, so why don't I'm happy to go through it if you like. Okay, so let's take a look here. So we have, this is unit 3 assignment, A7A. Okay, so they very annoyingly use W as the input variable. Okay, so here determine the point or points of inflection of each of these. Okay, so obviously we're going to have to work with the second derivative. So, I'm going to take the second derivative. Now notice here, I could bring down the 2, maybe make it a little easier. Okay, I use the ski slope rule. Either way, it doesn't really matter. I'll just stick with the way it's written. Okay, now by the way, what is the domain of this function? Can somebody tell me what the domain of this function is? Because normally I see a logarithm and I think, oh, greater than 0. But is that the case here? Who can argue why the domain of this function is not x greater than, or sorry, w greater than 0?
It can be all values because it's w squared. So the negative is multiplied by itself. So it's a positive.
Okay, so I agree with you on almost all those real numbers except one. There's
Except
still
0.
except 0. And of course, there's also w in the denominator. So let's keep in mind that, you know, we certainly, if we come up with something that's negative, that's actually fine here because I'm taking the logarithm of this squared term. Okay, so let's try to do this as quickly as possible. Again, please keep track of my algebra here. Okay, so derivative of ln of w squared is, again, and I'm going to do this more quickly now. It's just using the chain rule. So 1 over w squared, okay, times the derivative of w squared, 2w, okay, times the denominator function, which is w, minus ln w squared, times the derivative of the denominator, which is just 1, all over w squared. Okay, and a lot of nice things look like they're going to be happening here, because this w squared reduces with the 2 w's in the numerator since they're being multiplied. So I'm just left with 2 here, and then minus ln w squared, okay, all over w squared. Okay, so take a quick look, make sure I didn't make any silly mistakes. But in the end, that actually turned out to be not so bad. Okay, so let's
Tony,
take, yeah.
Sorry to interrupt. Quick question. Can you do the ski slope rule at
Yeah.
the top
Yeah,
to
that's what I
make it
talked
easier as
about.
well?
Yeah,
Okay,
and I'll go a
just
little
curious.
faster. Yep. All right, so let's take the second derivative. Okay, and again, makes sense to do that here from the simplified version. Okay, so here, obviously the derivative of the numerator, well, that 2 is just going to disappear, so it's going to be negative. And now the derivative of this thing here, well, we already took it. It's 1 over w squared times derivative of w squared, 2w, okay, times the denominator function, which is w squared, and then minus 2 minus ln w squared, okay, times the derivative of the denominator function, which is 2w, and all of this over w to the 4th. All right, so this is where now I'm gonna, you know, carefully simplify, because there's a lot of stuff going on. So I definitely see this w squared and this w squared, that's gone. Okay, so I'm left with negative 2w, and then here I'm left with minus, I'm actually going to leave this in the bracket because I see there's a negative 2w there. So I'm going to write an extra line. Okay. And the reason why I didn't bother distributing is because I'm seeing another common denominator. In fact, I'm not just going to take out a 2w. Can anybody see what I'm going to take out instead? To kind of make life a little simpler. What would make my life just a little simpler instead of just taking out 2w?
Negative 2w.
Why don't I take out a negative 2w? Why have to worry with all these negatives around? So here I'm just left with 1, and this is going to be plus. That's gone, so I'm just left with this here. So plus 2 minus ln of w squared. Okay. That goes, becomes cubed, and we can simplify that a little. Negative 2. So what do we have? We have 3 minus ln of w squared all over w cubed. Okay. And so now all we have to deal with when looking for points of inflection is this area here. Okay. So we need 3 minus ln of w squared to be equal to 0. Okay. And so I'm going to use my usual process here, which is to isolate my logarithmic term. So bring that to the other side. So we have ln of w squared is equal to 3. All right. And so here, change this now that I have a single logarithmic expression equal to a number. This is the result, w squared, which is equal to the base e to the power of 3. And now this is where we have to be careful that when we take, then it's funny because the one that the textbook kept was the negative one. We have to remember that when we're taking this square root, of course, it's going to be equal to plus or minus the square root of e cubed, which is the same as 3/2. Okay. Now I'm going back and I'm saying determine the points of inflection for each. Okay. So first of all, I have to confirm that these are indeed points of inflection. Okay. So let's set up our number line here. So I'm also going to put the 0 there because I want to make sure that, I know that the sign can change. So here we have square root of e cubed, square root of e cubed. This is negative. And just so that I know what to pick, let me put this in so I know what I'm working with here. So we have the square root, oops, turn that on, square root of e, whoops, let me try again. Square root of e cubed, and that's about 4.48. Okay. So if we pick -5 on this side here, -5, well, let's test. So we know that's negative and that's negative. So these two things are just going to be positive. So I just have to check that. So 3 minus ln of 5 squared, which is 25. And so that's negative. So it's going to be negative here. Now let's take something like -1. That one's a little easier. So negative and negative, so still positive. And here, ln of -1 squared is just going to be ln of 1. So that's 0. So I'm just left with a 3, positive. Okay, if you stick it in your calculator, it's fine, but I didn't need that. Should be similar here for +1. This, though, is going to be negative over positive. So I'm going to have my negative here. And then this one here, 3 minus again, ln of 0 is going to be positive. So this is going to be positive, negative. And lastly, this one here, let's pick +5. So again, negative over positive is going to be negative. And now just to check, even though we kind of should know what the answer is, 3 minus ln of 25, which we already know, is going to be negative times the original negative and positive. So in the end, we have two x values with points of inflections. Okay, so I'm running out of room here, so I'm going to do it here. So I have x equals, I think e to the 3/2 will be easy when we stick it into our equation. So e to the 3/2. And now what is our equation? It's ln of w squared. So ln of e to the 3/2 squared all over e to the 3/2. Okay, and why is this nice? Because the 2's cancel out, and what is ln of e cubed? Hey, these are inverses of each other. So they just cancel each other out. They just, essentially cancel each other out. So this is just going to be 3 over e to the 3/2. Okay, so there's 1 point. Okay. Yeah, that's what I'm doing. I'm plugging it into the original function. So somebody was asking, sorry, there's the original function. Okay. To find my y values. And now I'm going to do the same thing with, what's the other one? Negative e to the 3/2. And I suspect this one's going to be pretty similar because the y values, again, ln of, negative e to the 3/2, squared over negative e to the 3/2. So here, remember, this applies to both of these. So the negative is going to become positive and the 2's cancel out here. So I'm still going to be left with ln of e cubed, which is going to be 3 over negative e to the 3/2. And there's my second point. Okay. I mean, I guess I should put this as e to the 3/2, 3 over e to the 3/2, and then here, negative e to the 3/2, negative 3 over e to the 3/2, and those are my points. Okay, now this is likely to be a more complex equation than I would expect you to find the second derivative of. This is not nearly as simple as the previous one we did, and I probably wouldn't bother having you find the y values unless it was a curve sketching. Okay. But again, what I want you to see here is the actual process. You know, the calculus of it is pretty straightforward. Find the first derivative, find the second derivative, solve, test your number line. Where the complexity came in was all the algebra. So this is where having those good algebra skills comes in very handy. All right. Any questions on this other than that? Okay, so the other one that's got a video to it, I can go through it though if we want, was A10. Does anybody want me to still go through A10? And I'm assuming I just asked for 10A. I can't imagine I would have asked you to graph that. I mean, I can go through it. Okay, so this is Unit 3 assignment. A10. Yep, tomorrow's class is a review class. And I am trying to figure out if I can change the test to Friday, but there's still a teacher who hasn't gotten back to me. Is there anybody here who's taking physics? Is there a test on Friday?
I don't think we have any tests planned for
No?
this week.
Okay, so I think what I'm going to do is I'm going to move the test to Friday just so that people have an extra day to prepare. I will not, though, I will do new material on Thursday, but it's nothing that'll throw people off. But I do need to move ahead. So how do people feel about that? Do we like having that on Friday instead of Thursday?
Yes,
Okay.
a lot better.
Well, I know you do, but any other people?
So Tony,
Any other English people here? Yeah.
sorry to interrupt. So regarding the test on Friday, because you said you're starting a new section, so part of that section I'm going to assume is also going to be covered for that Friday's test, right?
No.
Oh,
What
okay.
I cover on Thursday will not be on the test.
Okay, sounds good.
Okay. So let's see, A10. I lost my sheet here. Okay, A10. Okay, so the graph of the function is a horizontal tangent and then, okay, so this is one of these that, you know, like one of them that was on the quiz. There's tons of these questions. The thing that's a little interesting about this one is that it's not a polynomial function. So here, hopefully I'll have enough room to finish this off. So we have the function ax plus b over x minus 1, x minus 4. And it tells us that it has a horizontal tangent at the point 2, -1. Okay, so here we have g prime of x. Well, I'll just say, so at, what is it? At 2. So we know that g prime at 2 has to be equal to 0. So that is that part. So that's going to be one piece of information. But since there's 2 unknowns, we need a second piece of information. That second piece of information is that, well, -2, 1 is on this function. Okay. Now, normally I would say start with the derivative. Why do we start with the derivative when we're working with a polynomial? What would be the reasoning for starting with the derivative when you're working with a polynomial? What does the derivative do to polynomials? Yeah, Ella?
It sometimes gets, or usually gets rid of the variable on the end.
Yeah, makes things simpler. You know, even if there isn't a constant, it'll make that, you know, that last term a constant. So in this case here, I'm not sure that the derivative is going to make my life easier. So that's why I'm going to start by inputting, what is the point? 2, -1. So when y is -1, x is equal to 2. So what do we have? We have a times 2 plus b over, so 2 minus 1, 2 minus 4. So what does that give us here? So 2 minus 1 is 1, -2, which I'll multiply to the other side. So that's going to be positive 2. So what we have is 2a plus b is equal to 2. Okay, so we have one equation for these two unknowns. Okay, so now let me use my derivative here. So first I have to find the derivatives thing. Can you see that it makes sense to multiply that denominator before I take my derivative? Okay, because when I'm taking the derivative of the denominator, I don't want to have to use the product rule, so I might as well just multiply it out. So let's take the derivative now. Okay, and so the derivative of the numerator is just a. Okay, it's constant times x, so it's a times x squared minus 5x plus 4. Okay, minus the numerator function ax plus b times the derivative of the denominator, which is 2x minus 5 all over the denominator squared. So x squared minus 5x plus 4 squared. Okay. Sorry, somebody's asking a question about how this was 2. So here, if I look at this here, 2 minus 1 is 1. Okay. And 2 minus 4 is negative 2. So the denominator here is negative 2, and I just multiplied that to the other side of the equation. Okay. And negative 1 times negative 2, that's where the 2 came from. Okay. Hopefully that's okay. Now, this is where this looks like a mess, and I could try to simplify this, but can somebody tell me why I'm not going to bother simplifying that thing? Why does it make no sense to simplify this thing here?
Can't you eliminate a factor of x squared minus 5x plus 4?
Oh, I can't because I've got a subtraction here. So there's no simplification I can do. Okay. Well, the reason why I'm not going to simplify is I'm only interested in the derivative at this one single point. So why go through all that hassle of simplifying? Yes, it's annoying to put 2 into all these things, although these will be the same. But to me, it doesn't make any sense to simplify when I'm only interested in the derivative when x is equal to 2 and I know the value is 0. So I'm just going to now put in, well, what is, let's do this first part. What is 2 squared? So I'm going to do this carefully because I already made one silly mistake earlier. So 2 squared is 4 minus 5 times 2 plus 4 is equal to negative 2. Okay. And by the way, I now know that that's going to be equal to negative 2 because it's the exact same expression. Okay. So now minus, well, x is equal to 2. So this is going to be 2a plus b. And now here, let's do, 2 times 2 is 2 times 2 is 4 minus 5, negative 1. And now this is something much easier to simplify than if I was doing it with all these variables. Okay, so this is where you can save yourself a lot of time. So this here, I'm just going to multiply to the other side of the equation. So it's just going to stay 0. Okay, and what do we have here? Well, we have negative 2a. Okay, here we have these negatives cancel each other out. So what do we have? We're just going to have plus 2a and then plus b. And look at what I have. B is just equal to 0. Okay. So that actually turned out to be quite nice. All right. But now, of course, now that I have the b value, I can just stick that into here to determine the a value. Because now what we have, I'll call this equation 1. Okay. Equation 1, we have 2 is equal to 2a plus 0. So a is just equal to 1. Okay. And in the end, it turned out to be fairly easy, despite the fact that it looked like quite a mess when we took that derivative. Okay. But what really helped us out was to not bother simplifying this version, but the one with the 2 inputted into there. All right, any questions on that? Okay, and again, I will say, a question like this, I didn't try, notice how I didn't try to necessarily foresee where this was going. You know, I made the assumption that working with the function would be easier, and it was, because the function was pretty straightforward. You know, working with the derivative took a little more time, even though in the end, it's simplified to something quite straightforward. All right, any questions on this or anything else before we end off? No? Okay, so again, definitely please keep working on that quiz. Make sure you're able to do each and every one of those questions. All right. So I'm going to stop recording.